In this video, we're going to take a look at how anhydrides react, and they look like kind of a large functional group to deal with. But if you know the chemistry of acid chlorides, the chemistry of anhydrides really isn't much different or much more difficult. So what you want to do is pick one of these carbonyls, and it really doesn't matter which one, assuming you have a symmetric anhydride. Think of that as an electrophilic carbon, just like an acid chloride. So if we compare this, here's our electrophilic carbon in the acid chloride, our electrophilic carbon in the anhydride. And then in the acid chloride, Cl is the leaving group. Well, in the anhydride, it's a bigger thing, but this whole acetoxy group is a leaving group. And don't forget, sometimes you'll see this group abbreviated as just OAC. To simplify it. Now, keeping up with our comparison of acid chlorides, if you took some nucleophile with a hydrogen on it, so that could be something like, we did water, alcohols, or amines, what we found would happen is that the group would replace the chlorine, and you formed a new carboxylic acid derivative. And there were some subtle details, like for the water or the alcohol. You could do this under acidic conditions if you wanted, or what we learned to focus on was just using pyridine to speed the reaction up, or with the amines, you would use two equivalents of the amine. Well, you can do the same thing with anhydrides. So now, instead of losing chlorine as the leaving group, we'll lose this whole acetate group. But it's very similar that we can use a nucleophile that has a hydrogen on it, because the hydrogen gets lost and the nucleophile is added to the carbonyl. And likewise, we can use the same nucleophiles like water, alcohol, or amines. Let's go through one of these for something you may already remember. Way back when we talked about aromatic reactions, we took aniline, added acetic anhydride, and we formed acetanilide. We get that bulky amide group on the aromatic ring. Now this was written a little bit differently than just starting by writing the acetic anhydride and adding an amine nucleophile, but it means the same thing. We're mixing those two things together. So let's go through how this reaction works. I'm going to abbreviate aniline as just PHNH2. And just to keep it consistent with the other reactions we've done, let's start with acetic anhydride as our primary reagent. And here's our amine. And I'm going to treat this carbon as the electrophilic carbonyl carbon. So we add our nucleophile to the carbonyl carbon. We get this intermediate. Now we can push that lone pair down and lose the O- group. So we get that. And here's the leaving group that came off, this acetate. From here, now our aniline is the base that's around. So what we can do is just use another molecule of it to take the proton from the nitrogen. And we get our product. So this looks a little different than the product up here just because we've abbreviated the phenyl group. But rest assured, if you do draw it out fully, you have your aromatic ring, your NH, and the carbonyl on that. So this is the mechanism by which this reaction that we learned before occurred.